Hello, Physics 2B, Section 7. We are in Week 8, Tuesday, March 23rd. And we have a discussion today, we have a warm-up today, and you are watching the lecture video, which is not there yet because it's still being recorded in my frame of reference. Okay, but you'll have a link like that there as well. Everyone should have their corrective due and done from last Friday, and I'm grading those after this video. I might be finishing them tomorrow, but you'll have your corrective grades done by then. Just remember that you should have both a second submission on the unit test and your handwritten corrective submitted. If not, then you'll be getting an email from me. Okay, so that's looking backwards. How about looking at today? Today, we have a discussion and a warm-up. Our discussion, which is due by Wednesday at midnight, is to look at Chapter 24 and try to do a problem that requires calculations. A lot of what we've been doing so far has been just focusing on directions and focusing on these two right-hand rules. I want you guys to get out of that shell a little bit and see what you can do in terms of some calculations as well. And not just something that is just a straight up answer. Attempt a two-line problem so that it's not just a direct plug in numbers to this one equation. You'll have to do some manipulation to get a result. Okay, so that's our discussion. A problem from the end of that chapter, or helping someone else with their attempt on their problem that they chose. Next, we also have a warm-up, and this warm-up is really seeing how well you guys are doing with those questions from the Stephen Murray right-hand rule practice. A lot of questions pulled from there to see what you can do. How many? We're looking at 10 questions, no time limit, but you only get the one attempt. So be extra diligent in what you do and what you choose on your answers to those. It's multiple choice, but I put down basically all the choices I could think of on every single question. So in that way, it's quite open-ended as far as the responses that you could give, much like it is on the Stephen Murray right-hand rule practice page. Okay, so since it's a single submission quiz, make sure that you double check your work before you press submit, so that you get every point on the problems that you know and deserve the points on. This is due Tuesday night, midnight, and by midnight I do mean 11:59 p.m. All right. So that's our assignments. And what we're doing here is a lot of stuff that was in the pre-recorded videos from last week. Okay. Last week we definitely went over magnetic sources. That was huge. Okay. And with those sources, we considered the Earth as a magnetic field source. We considered magnets as a magnetic field source. We looked at a wire of current being a magnetic field source, whether it be a line of current, which is what this page is all about, lines of current, or if it was a loop of current. or many loops of current stretched out into a slinky-like shape. Then, on Thursday, we focused on the magnetic forces. And those magnetic forces involved looking at the forces right-hand rule, which is distinct from the sources right-hand rule. There's many different versions of it available on the internet, so I'm hoping that most of you guys went with the version that I have here. Otherwise, you need to be consistent with whichever version you found elsewhere. But I highly suggest that you find one right-hand rule and stick with it when it comes to the forces right-hand rule. The sources right-hand rule, on the other hand, has a lot more versatility to it, but it's only for a current creating a magnetic field. This brings us to where I want to start today. This might have covered it a little bit last week, but I think it's worth repeating this stuff even if I have. The forces right-hand rule leads to circular motion. And this is largely due to the fact that the magnetic force is perpendicular to the velocity of the charge. And that's why we have our hand set up into these right angles, so that we have the velocity and the force always have a right angle between them. Always 90 degrees. With that in mind, what can that force do? Because when we think about something we learned from Physics 2A, hopefully, we should remember about the work that a force can do. Where a force multiplied by the distance that the particle travels is the work done by a force. But there's a limitation. It's only the part of the force that is perpendicular to the motion. Okay, so work only occurs if the force is parallel with the motion. And I just said the opposite thing. Magnetic force is always perpendicular, but in order for work to be done, it needs to be parallel. Therefore, the work done by a magnetic field is zero. More specifically, this is the work done by a magnetic field on a point charge moving through a magnetic field is always zero. Okay. Little extra condition there about it being a point charge, but other than that, this is what happens when we have this consideration of parallel and perpendicular to consider. What does this mean as far as what the magnetic field can and cannot do? Well, if we look at how much energy is going to be transferred to the kinetic energy by some magnetic field, we already know that the work is going to be zero, so the kinetic energy stays constant. No change, no increase, no decrease. In other words, the charge will not speed up, and the charge, spell that again, charge will not slow down. But the magnetic field still does something. To the velocity. At this point, remember what you learned in Physics 2A about the distinction between speed and velocity. The speed is a matter of how fast something is moving. The velocity is how fast, but it also includes the directionality. So let's set up a magnetic field here. I'm going to have a magnetic field pointing out of the page. That's my magnetic field. And I'm going to repeat a few rows of this. There we go. Good enough for me. So we've got a magnetic field, and we're going to have a charge move into it. Okay, it's going to be a positive charge, and it's going to be moving with some velocity to the right. As such, using the right-hand rule, I put my fingers to the right along the velocity. I have my palm pointing out of the screen. So since I have my screen horizontal, it kind of looks like I'm holding a plate like a waiter might do. And as a result, my thumb is pointing down the page. This is the direction of the magnetic force that is being applied to that charge. And that force is going to change something about that charge. It's going to make it undergo circular motion. Okay. Because once it starts turning a little bit, it has a velocity in this direction now. And when I do the right-hand rule again, I get a force in that direction. It keeps on turning, and the force continues to be perpendicular to that motion. Okay. So the magnetic force can't speed it up because it's not in the same direction. It can't slow it down because it's not in the opposite direction. This perpendicular force can only change the direction of motion of our charge. This results in circular motion of charges. So when the force applied is perpendicular to the velocity at all times, and the force is constantly turning the particle, remember that the centripetal acceleration is the speed squared divided by the radius. This is something that I double-checked to make sure that you guys had at least heard of during the "Are you ready?" questions at the beginning of the semester. So we've got circular motion. Of some radius of motion due to some force that's always pointing inwards. And that magnetic force is equal to Q, V, B, and I'm not writing the sine theta just because I'm going to assume nice perpendicular things for this situation. All right. So I can use Newton's second law, which is that the net force is equal to the mass multiplied by the acceleration of the particle. The net force is only the magnetic force, because that's going to be our only force acting on the particle for this example. QVB. The mass is accelerating. Its acceleration is purely centripetal. Okay. And I go back and forth between an uppercase and lowercase r on this one. I'm using an uppercase in this right up here. 1/4 of the speed cancels out of both sides. And I can rewrite this to determine the radius of motion to be mv divided by qb. This is the radius of motion. So the radius of motion tells us just how big of a circle we're talking about. Okay. And you could have a radius of the circle like we have in this example right here. Or you could have a much, much smaller radius if you had motion like this. Okay. So two different circles that are different sizes. This is our big circle. And this is our small circle with a small radius of motion compared to our big radius of motion. In fact, when I go all the way down to the small circle, the big circle looks almost like a straight line. Barely any turning happening there at all. So when we zoom in on big circles, for large stretches, big circles look like straight lines. What does that mean for our equation over here? Okay. Well, I'm going to look at this in terms of physics 2A stuff first. And I'm going to do that because of the numerator. That's 2A stuff. More specifically, that looks like the momentum. It's actually mass times speed, but our momentum is mass times velocity. So it's the magnitude of our momentum. If something has a large mass and is moving very quickly, so it has a large momentum, then it's likely to have a larger radius of motion. Okay? So picture a very large bus that's moving quickly. That thing is going to be very difficult to turn. Since it's very difficult to turn, it's going to look like it's just going straight instead of doing an easy turn. Okay? So the bus will definitely be difficult to turn with its big mass and likely large velocity. Okay? It's probably not charged up in a very large magnetic field either. This is our 2B stuff. Okay, we had a whole unit where we were talking about what a charge is and how it interacts with electric fields. Now we're talking about how it interacts with magnetic fields. So two big things about physics 2B in the denominator right there. If you are in a situation where the 2A stuff dominates, like with that bus, you got a big radius of motion and it's basically going straight. But if you've got a 2B dominant situation, like an electron moving in a magnetic field, then that electron is going to have a very small momentum because it doesn't have much mass at all. And so there's actually an experiment in this class that's all about considering the motion of charges in magnetic fields and looking at the different radii of motion for them. Okay. because their circles will be small enough that we can actually see the path of electrons moving in a magnetic field. Right. There's an astronomical application of this. The astronomical application is the aurora borealis, and it's actually not even limited to the aurora borealis. It's also the aurora australis, the Jovian auroras, the Saturn's auroras, anywhere where you have charged particles moving and being deflected by a magnetic field. That's the application. Okay. Here's what I mean by this. So I copied down the Wikipedia page for the aurora effect. Okay. And maybe you've seen it yourself. Maybe you've just seen it as someone's Zoom background. But this is what this greenish stuff and sometimes reddish stuff is in these images, where we're looking at something that's in the atmosphere, emitting light, and it doesn't quite get all the way to the ground. Okay? It's absolutely freaky and gorgeous all at once. Okay? We've also observed it from above. When the International Space Station was flying over the South Pole, it was able to see the aurora australis from above. Okay. And if you check out the Wikipedia page yourself on the aurora, then you'll be able to see these 3 videos, where it's video of the space station flying over and towards some significant aurora events. Really cool stuff. Really pretty stuff. Something that I haven't seen in person yet, and here's why. Aurora events mostly happen in this blue region. Okay. I've heard of them occurring as far down as this red region, but usually you need special equipment to see them down there because they're not as bright when they do occur. So something important about it is that we're dealing with the polar region. Why is that? Why is it centrally involved with the polar regions? Let's take a look at the Earth's magnetic field. Okay. Here we have the Earth's magnetic field already drawn out for us. That's going to save me a little bit of time so I don't have to draw it myself. Although I do enjoy drawing the Earth's magnetic field and the continents, but not this time. The sun does more than just shine light on the Earth. Okay? So we got sunlight coming in. In addition, you can have charged particles coming from the sun. So electrons, protons, alpha particles, ionized gases, ionized atoms of all sorts, coming from the sun to the Earth. Okay? And as they approach, they will interact with the Earth's magnetic field. I'm going to have one positive charge approach the Earth there. Okay. Another one approach the Earth like so. And a third one approach the Earth way down here. Not B, V. What's going to happen to the charge as it reaches this magnetic field? Well, the magnetic field we already have drawn upwards like so. So I can use the forces right-hand rule to determine the direction of the magnetic force on this charge. I put my fingers along the direction of the magnetic field. Sorry, try that again. I put my fingers along the direction of the velocity, which is to the left. I rotate my hand so that my palm is pointing away from me. Okay? It looks, from my perspective, like I'm pushing something up the screen. And as a result, my thumb is pointing into the screen. That into the screen thumb means that's the direction of the magnetic force due to this magnetic field acting on that charge coming in. What is that going to do? Well, that is going to push the charge into the board, and it's going to go around the back, back up the front, and across the top, and start to undergo circular motion. Okay. In effect, this charged particle gets stuck in the magnetic field because it was coming in, and all that motion went from coming in towards the Earth into some circular motion. That's going to happen for much of this region, where charges will get stuck as they are trying to approach the Earth. But that magnetic field protects the Earth so that you get charges stuck in circular motion. This region is called the Van Allen belts. The Van Allen belts are regions where a whole bunch of charged particles are stuck in the Earth's magnetic field, just moving in circles over and over and over and over. Now, sometimes charges will hit each other and they'll deflect one out of the region, but there's actually two Van Allen belts, one farther out and one closer in. Okay, so two significant regions that go all the way around the Earth, all because of charges that get forced into circular motion by the magnetic field. This is something that astronauts care about when they go to the moon, or in similar situations like that. We care about it on the surface of the Earth because it protects the surface of the Earth from getting random charged particle storms hitting the surface of the Earth, which is really good for our electronic infrastructure. Let's check out the next one. Up here, remember that our magnetic field is along the screen, this green line. Good. There are two components of the velocity that we care about. One of these components is parallel to the magnetic field, and the other part is the velocity that is perpendicular to the magnetic field. Two components of the black vector. The blue vector, the parallel vector, because that component is parallel to the magnetic field, it experiences no magnetic force. So the charge will continue to move along Earth's magnetic field. So it will go along the magnetic field line like so. But there's also the red component to consider. The red component here is completely perpendicular to the magnetic field. As such, there will be a magnetic force associated with that motion and that magnetic field. I take my right hand and I put it in the direction of that red vector. I then rotate my hand so that my palm is pointing along the magnetic field. And that leaves me with my thumb pointing into the board, into the page, into the screen. What does that force do? That force is going to cause the red to undergo circular motion. That will push it into the page, but it will undergo circular motion from there. So it'll go around the back and back up the front and around. When I combine these two, when I combine the circular motion for the red component and the linear motion for the blue, I get that the charged particle is going to come in and it's going to go under and around and around. And we get this helical motion of the charged particle moving circularly around and along the magnetic field line. And it follows the magnetic field line all the way down to until a new force interacts with it. That new force will be when it hits the gas in the atmosphere, at which point it'll hit likely nitrogen or oxygen. If it's in the high atmosphere, the hydrogen at that elevation, its temperature, its pressure, and other considerations mean that it will emit a red light, and at lower elevations, a greenish blue light will come from the nitrogen and the oxygen at those elevations. That is what we're seeing. We're seeing the oxygen in the atmosphere at the high elevation, and we're seeing the nitrogen and the oxygen at the lower elevations. Boom. This is the aurora borealis, and you get it in this region. So Canada, Alaska, Russia, Greenland, Iceland. One of my bucket list things is to go to Iceland and see the aurora borealis sometime. It's a big goal. What about this one down here? What is it going to do? Well, we still have those two components to consider. We have the component that is parallel to the magnetic field. Technically, it's anti-parallel because it's in the opposite direction of the magnetic field. The magnetic field is in this direction. But the velocity's parallel component is in the opposite direction. That's fine. Parallel, it still counts as parallel. And then the other component, V perpendicular to the magnetic field. The blue component is undeflected. It continues to be parallel to the magnetic field, or anti-parallel as it may be. And the red component experiences a magnetic force. I put my fingers along the red. I rotate my wrist so that the magnetic field is pointing out of my palm. And it kind of looks like I'm in the middle of a breaststroke in the pool. So I've got kind of reaching my fingers forward and I'm just about to pull them outwards. As such, my thumb is pointing into the screen so that my magnetic force is into the screen. This causes the particle to undergo circular motion into the board, out of the board, into the board, out of the board, as it circulates in, out. Let me see if I can get my rhythm correct on this one. There we go. So the important consideration here is that the motion parallel to the magnetic field is undeflected, and the perpendicular component gets this circular motion, which combines into helical motion. That charge makes it all the way to the pole. And people in Australia, maybe in Cape Fear and Cape Hope, South Africa and the Falkland Islands, and especially in Antarctica, can all see the aurora borealis occur in that region. But it's not the aurora borealis there, it's called the aurora australis. This can occur on other planets too. Okay, here's the aurora australis. So you can see it really making a big circle around Antarctica. So not quite high enough to be seen in Australia or New Zealand. It's really just going to be something that's seen in Antarctica or over the ocean. It can be seen on other planets as well. On other planets, such as Jupiter, there's Jovian aurora events, because Jupiter is the planet with the largest magnetic field in our solar system. It's not the strongest magnetic field, but it's the strongest magnetic field of any planet in the solar system. The Sun takes top honors for the strongest magnetic field in our solar system. So we can see aurora events at its poles, which are a recent find because it's kind of hard to see exactly what's going on there. Okay. It was first studied with radio emissions over 50 years ago. And as such, with new technologies, with missions where we actually sent satellites out, Cassini, Galileo, etc., we were able to take shots at exactly what it looks like in these charged particles hitting the Jupiter's upper atmosphere. Saturn II. This one's a little bit more awkward to see. The shape of Saturn is kind of like this. Okay. Really, really zoomed in on one part of it. Because we're looking at this from the backside, the dark side of Saturn, so that we can see the aurora event here near the pole. And all the stars are streaky in the background because it took 81 hours to get a good visual of this. So they kept the lens open on the camera for 81 hours to collect the light. It kept its camera focused on that part of Saturn, and because of the motion of Saturn and the Cassini spacecraft, the stars in the background seem to move. Okay. Uranus and Neptune also have those. Not quite as much though. Uranus and Neptune do have significant magnetic fields, but it's so far away that not as many of the charged particles get all the way to those planets. Okay? So those ones don't get the magnetic field, the aurora events. And it talks in here about Venus and Mars as well, if you're inclined to see what's going on with those. Mercury would not have an aurora event at all because it basically has zero atmosphere. The sun has blown all of the atmosphere off of Mercury. Similar issue with Pluto. It doesn't really have any atmosphere, it's just got a solid surface. It's too small to hold on to any gases on its surface. Okay, and a load of references associated with that. Okay. And that's our big example of charges moving in magnetic fields, and a way that we can see the effect of them by having those charged particles hit some gas and cause that gas to emit light. There are other considerations we have for the magnetic force. We've already gone over force is equal to QVB sine theta, and that's for a charged particle moving through a magnetic field. Here we have magnetic forces equal to Bilsin. So you've got a magnetic field, and there's some current in that magnetic field. And we saw that a bunch in the right-hand rule practice, where we treated the current like a charge motion, because that's fundamentally what it is, along some length, and that caused the magnetic field caused some sort of force on that wire. Let's consider a few situations about how two different wires will interact with each other. I'm going to start with one wire that has a current to the right, and a second wire that has a current also to the right. They both create magnetic field in the region. Using the right-hand rule, I'm going to start with the red one, because it's number one. I put my thumb in the direction of the red current, and my fingers naturally point towards me over the top. Towards me, that is magnetic field out of the screen. And then my fingers naturally wrap around my thumb so that they then point into the screen on the other side. And that'll be true for this entire side below our red current 1. Next, the blue. The blue is also creating magnetic field. And it's creating magnetic field in the same region as each other, but I'm going to put it off to the side so it's easier to see what's happening. The current is to the right, so it also creates a magnetic field that's out of the board there and into the board below. And at all points above, we get out of the board. These magnetic fields will cause forces on the other charges. I'm going to say that again, making sure I get it correct. The magnetic field created by current 2, so B2, will interact with I1 at this location. So we've got a magnetic field pointing out of the page. We have a current to the right. Another one that's a little difficult to get your hand in the right direction for. So if you just kind of put it on the side of your body, it's a little easier. So current to the right, so fingers to the right, palm pointing out of the screen, and I end up with my thumb pointing down the page. That's the direction of our magnetic force. Which magnetic force? It's of current 1 acting on, current 2 is the blue one, acting on current 1. That is, I can do an extrapolation from that. The extrapolation I get from that, if I remember physics 2A stuff correctly, remember that the force of A on B is equal and opposite to the force of B on A. When I go over here, I'm expecting the exact opposite result. I'm expecting that the force of magnetic force, more specifically, of 1 acting on 2 to be up instead of the other one's down. Let's see if we can confirm that. Our current is to the right, and our magnetic field is into the page. I put my fingers to the right. I put my palm downwards towards the screen, which is one of the easier ones we've had today, and my thumb naturally points up the screen. Exactly what we expect. So, using our right-hand rules, we had to use both the sources and forces right-hand rules to get this one right. We get this interesting result. When currents in nearby wires are in the same direction, comma, then the wires attract. I see the red one being pulled towards the blue, and I see the blue one being pulled towards the red. Current in like directions attract. Completely opposite of what you get from the electric forces, where you get likes repelling. Here we get likes attracting. How strong is this force? Well, our magnetic force of, let's do 2 on 1, 2 on 1. How strong is this? Well, I'm going to start off with the force equation. That force equation is I, L, B. I'm talking about the magnetic field, so this is B2. B2s, and so I'm looking at this region up here. And the current that is experiencing the force, that's I1. And that length 1. A note about that length. That length is going to be whatever the length of the wire is. And one more distance to be aware of is the distance between the two wires. I can do a substitution for B2. B2 is the magnetic field from a line of charge. So I can say that the magnetic field 2 is equal to the permeability of free space multiplied by current 2 divided by the circumference, 2 pi radius, and the radial distance is actually d. I'm going to substitute that in. And I get I1 L1 multiplied by mu naught I2 divided by 2 pi d. This is usually written in a slightly different form, where the magnetic force per unit length is equal to mu naught I1 I2 divided by 2 pi d, if it's the magnitude of the force. That way I don't have to worry about the directionality, and the magnitude of those two are the same because they're Newton's third law pairs. So 2 on 1, 1 on 2, same magnitude. So we can use that to find out just how much force is pulling these two together. Let's figure out what goes on when we have the opposite occurring. The opposite will be when the currents are in opposite directions. So I'll have a current to the right like so. I'll have a current to the left like so, opposite directions. I1 is going to create magnetic fields that are out of the board on this side and into the board on this side. Similarly, I2 is going to create magnetic fields that are out of the board on this side and into the board on this side. I can then use the right-hand rule to find out the direction of the magnetic force of one on the other. Here, we have the current going to the right and the magnetic field pointing downwards into the screen, which leaves my thumb pointing up the screen. That's the magnetic force of 2 on 1. And that is a repulsion. It is opposite, just as I predicted. For the other one, we've got the magnetic field into the page, and we have the current to the left. I put my fingers to the left for the current. I put my palm down towards the screen so that my palm's pointing into the screen. And this is the most comfortable one yet for all the right-hand rules I've done today. And I end up with my thumb pointing down the screen. That's the force of 1 on 2. And we see the repelling happening again. So when the currents are in opposite direction, opposite directions, you get that the wires repel. Let's do one more. We've got the two different versions of parallel. Now let's consider perpendicular. What if current 1 is to the right like so, and current 2 is up like so? Current 1 is going to create magnetic field that is out of the board on this side and back into the board on this side. I2 is going to create magnetic field that is into the board on this side and back out of the board over here. I'm going to figure out the direction of the force at all 4 locations. Over here, the current is to the right, so I put my fingers to the right. The magnetic field is into the page, so I put my palm into the screen. And I end up with the thumb and my force in that direction. On the other side, we have our current going to the right still. But now my palm needs to be pointing up. So I'm in that whiter position again. Like I'm bussing tables or something. And I end up with a force in this direction. Both of these are the force of 2 on 1. Force of 2 on 1. Depending on what side of the wire you're on, you get opposite directions. And since this is symmetric, we end up with those two forces cancel. Let's see if it happens to the other one too. Up top, current going up the page, magnetic field pointing out of the page. So I'm looking at my palm right now. And I'm looking at my palm with the force being to the right, because that's the direction of my thumb. That's the force of 1 on 2. On the other side, current is still going up the screen, and my palm should be into the page. So I'm basically just looking at the back of my hand now, with my thumb pointing to the left. That's also the force of 2 on 1 magnetically. And they are equal and opposite. Okay. Again, there are magnetic forces acting in this situation, but they cancel out. So if the forces cancel out, well, then the net force is 0 and the magnetic force cannot move the wires. That's not entirely true. There is something else that they can do. If you take your pencil or your pen or something, or your stylus, whatever it is you're writing with, and you put it on the table and you push it here like so, and you push it here like so, it's going to rotate. This is a torque situation. But the forces do cause a net torque that rotates the wires. How does it rotate the wires? Well, I see these sides rotating towards each other. I see the other sides rotating towards each other. They rotate the wires to align the currents. And their magnetic fields. Torque. Okay. This is a big thing about magnetic fields. So magnetic fields do not lead to translation when it comes to point charges and lines of current. Instead, it leads to circular motion and rotations. On Thursday, we're going to explore this idea of these torques a little bit more, looking at what happens when you have a loop of current in a magnetic field. What happens? I'll be defining the idea of a magnetic moment. We'll be talking about torque. So make sure you have the concept of torque ready in your head on Thursday. And we'll be looking at fundamentally what is a compass. What makes a compass on a macroscopic scale, and also what makes it a compass on a microscopic scale, more specifically on the atomic scale. Okay, and then we'll be able to talk about our floating frogs and be ready to talk about a lot of other material after the break, because we got spring break coming up. Okay, so we've got a few things ready for Thursday. Okay. That's the lecture for today. Some applications of magnetic fields and what they do to point charges and what they do to lines of current. Make sure that you did everything correct for your corrective. Make sure that you submit your warm-up today. And also, make sure that you complete your discussion by Wednesday night. Okay. That's it for today, Tuesday, March 23rd. Good luck with your discussion and warm-ups. Let me know if you have any questions, and I'll talk to you more on Thursday. Take care.